So good morning, students. So let's discuss optimal binary search tree, or OBST, or you can say optimal binary search tree, or BST. Okay. So this is a same problem actually we were talking about in our last previous lectures. We were talking about dynamic programming mainly. So in dynamic programming, we have seen that how to solve one optimal problem or optimization problem using dynamic programming when the same problem is solved using exhaustive search or exhaustive technique, where we need to uh, have time complexity like or exponential, or we need to spend exponential time for solving that problem using exhaustive search or exhaustive technique. But dynamic programming reduces that exponential time complexity into polynomial time complexity. So that we have seen for certain problems we have already discussed, like matrix multiplication, rod cutting problem, and longest common subsequence problem. So in all these problems we have seen that how optimal solutions we can obtain after applying dynamic programming using polynomial time runtime actually. And also we have discussed that what are the main characteristic or properties an optimization problem must hold so that we can apply dynamic programming. So today we'll talk about optimal binary search tree. So before going to the detail of the problem, let's little bit discuss about when we need to use this one, this optimal binary search tree structure or data structure, for which kind of problem we need. So we have the idea of binary search tree, that what it is actually. So we have set of keys and these are sorted in order, and then we can create or develop a tree. That tree actually helps us to find out a particular key in login time. Okay, so that is actually one advantage. Instead of using sequential searching and other searching techniques where we see that time complexity is order of n, but binary search tree gives us order of login time for searching one particular key. Okay, so it is called binary optimal binary search tree because suppose we take one example that we need a translator for translating English words into some other languages, suppose French language. Okay, so for each individual English term, there must be one particular French term. Okay, so we every time when a particular uh, English term we have, we need to find out the corresponding repository or data structure to find out the corresponding French term. Okay, so that we can do. But if we use sequential search, that is both situation. We don't need to use it because we have binary search technique. So we can create one binary search tree for it, and we can reduce the searching time to order of login. But even you see, if we do this one, the problem is that some terms like the and some other terms like is and some articles, some verb, common verbs, which appear very frequently in a text. Okay, and some words or terms in English text, they appear very less, like irregular or infrequent way. So if we keep the words or the terms, English terms in the text which are very frequent, far from the root of the tree or the binary search tree, so every time we need to spend a lot of time for finding that successful search. Okay, and the terms which are actually infrequent, if they are kept near to the tree root, so that is actually not a good idea of organize the tree. So the idea may be like that, that the frequent word which appear very frequently in the text, we can keep them nearer to the tree so that that will reduce the time complexity or searching time. Okay, so based on this idea, the optimal binary search tree technique or the concept has been introduced. But we will see that there may be many binary search tree for a particular set of keys. So which particular binary search tree is an optimal, or which set of binary trees are optimal, because there may be more than one optimal binary search tree for a same set of keys. So which one is the best? That is the objective to find out in this problem, that which one is the optimal binary search tree for a set of keys or set of words we are currently considering. Okay, so we'll be talking that part here. So we know about binary search tree, as we already told and we have studied in our earlier classes. So their set of keys are stored in such a way that the time complexity becomes order of log n. Okay, but sometime if we now use normal BST or binary search tree, it is not always gives you order of log n, because if the tree structure is queued kind of structure, then the worst case time complexity may be order of n. So that may be worst case. But if we use a balanced binary search tree like red black tree or ABL tree, so these are balanced binary search tree. Okay, so in this binary search tree, if we use this data structure, so the time complexity always remains order of log n. Okay, so this is the basic thing we want to discuss here. And other point, as I already mentioned, that the frequent use data, or the data which frequently appears in the text, they must be placed nearer to the root and or closer to the root. And the other elements which are least frequently used words, those words can be stored or kept far from the root or at the leaf level, actually you can say. So the thing is that, as I said, that there are many possible ways of creating a optimal binary search tree. There may be many number of binary search tree. So which one is the optimal, or which are the optimal? So we need to construct each and every binary search tree, possible binary search tree for the set of keys, and then we have to check it. So when we do this one, actually the total time complexity become exponential, because we need to perform exhaustive search or exhaustive technique to check whether a particular binary search tree is optimal, or it is better than all the previous binary search trees we have constructed till now. So in that way, this exhaustive search will take exponential time for checking out all the possible binary search trees. Just a minute. Okay. So actually I need to change this. Is my slide visible? Please confirm.
Yes, sir.
Okay. So so what is an optimal binary search tree? So here the optimal binary search tree, what you're talking about, it consists of set of keys k, which consists of some keys like from key1 to k1 to kn. Okay. So all these are, we are assuming that distinct. So it's not that always like you'll have a successful search, because for suppose the example you have taken, in the example there may be some words, English terms, for which we could not find one particular or corresponding French term. So for those terms, we will reach to some unsuccessful search. So to represent that unsuccessful search, we add some dummy keys which denotes the unsuccessfulness or unsuccessful search for a particular key. Okay, so these dummy keys are denoted by these D0, D1, D2, Dn, and you see that each Di value is between Ki minus 1 to Ki. Okay, so this denotes that the value D0 is less than equals to K1, D1 is less than equals to K2, and greater than equals to greater than equals to K1. So in this way, we use some dummy keys for representing this unsuccessful search. Okay, so and along with that, each key is associated with one particular probability, that the probability of finding or searching for a particular key Ki. Okay, so Pi is denoting one probability associated with a key Ki, that it denotes the probability of searching for key Ki, and D0 is denoting the probability of unsuccessful search of one particular term that is less than K1. Okay, similarly, D1 is one successful search which is greater than K1 but less than K2. So all these terms, all these keys and dummy keys are associated with some probabilities of searching for a key, whether it is successful or unsuccessful. So Di is denoted associated with one key, probability, that is Qi. Okay, so in this way we can find out that the total probability of successful and unsuccessful search for all the keys and dummy keys is 1 actually. So we can denote these things in this way, that the probability of all the valid keys, sum of all the probabilities of the valid keys and sum of the probability of the all the dummy keys is actually 1. And here you see that the dummy key starts from D0 to N. Okay, so one more dummy keys. So D0 is denoting the smaller key values than K1, and Dn is denoting that the greater value than Kn. Okay, and the total probability is actually 1. Why this probability is important? Because we want to find out the expected time comes in the searching time, expected cost. Because we don't know that which particular key will be searched or looking for a particular time. But based on the text given as input, we know that how many times that particular key is present in the text, and based on that we can calculate the probability of each terms present in the text. So that's why each particular key or dummy key or term, you can say, is associated with one probability value, Pi or Qi. So we are interested to find out the expected search cost. So what is the search cost? Search cost is something that the number of nodes we need to visit. Okay, we need to search. That is the search cost. Okay, and as each node is associated with probability, we can find out the expected search cost for the total tree or the entire tree T. Okay, so when we visit the number of nodes for finding a particular key, so that would be the depth of the node plus 1. Okay, so depth of the node plus, because suppose we have a tree like this, and suppose we want to find this node, so we need to visit how many nodes? 1, 2, 3. So the depth of this is 2, and this for one more node we visited, that is 1 plus 2 plus 1, that is 3 nodes we visited. Okay, so in this way we can find out the total search cost is equals to the successful search for all the key value ki is like this: depth of the key ki plus 1 and into pi, the probability associated with each key ki. Similarly, for each unsuccessful search, we find from I0 to n, and for the depth of each di dummy key plus 1 for the root, or you can say the first node of the subtree, into qi. Okay, so all these together, what we get, that this part, the summation of I equals to 1 to n pi for this part, and for this part we'll be getting the previous expression, this one, and that will be 1 actually together, all together, and this is the next part. So the expected search we can find out in this way. Okay, so we want to construct a optimal binary search tree which will give you the minimum expected search cost. This is our objective. So as I said, there are many number of trees we can construct. So we need to find out the best one or optimal one. So we can have one example for 5 keys. Actually, we have 5 keys: 0, 1, 2, 3, 4, 5, and 0 is actually denoting this I0 for the unsuccessful search, or it is the key value we are trying to find out, which is less than key 1 actually. So each node is associated with the probability, this, and each dummy key is starting from D0 is associated with one particular probability, and this one. And we have two optimal, or you can say optimal binary search trees, and we can calculate the expected search cost for this tree is 2.80, and expected the search cost of this tree is 2.75. So if we construct these two trees, so we will be considering this one as an optimal search tree, and we will be using this one for our experiment or for our use actually. So these trees are optimal. Now, how we are getting this one? This cost, expected search cost, we can calculate in this way, that this table already we have seen. Now, suppose we want to find out the expected search cost of this tree. Okay, so what we'll do, we'll take the probability expected search cost for each particular node. Okay, so we need to calculate the depth of the each tree, depth of each node actually. So k1, depth of k1 is 1. Okay, depth of k2 equals to 0, depth of k3 equals to 2, depth of k4 equals to 1, depth of k5 equals to 2, depth of d0 equals to 2. So in this way we can find out the depth of all the nodes from our basic knowledge, okay, of tree and their nodes and their depth. Now, as we already know that the expected search cost for a node actually k1 is the depth of the node plus 1 into the probability of that node. Okay, so depth of k1 is 1. So here this one actually plus 1 into the probability of k1. Probability of k1, that is p1. So probability of k1 equals to this 0.15 into 2, that is 0.30. Similarly, depth of k2 equals to 0, so it will be 0 plus 1, and this will the probability of p2. So p2 is 0.10, so it will be 1 into 0.10, so this will be this one. So in this way we can calculate, suppose we want to calculate d3. So depth of d3 is equals to 3. So the expected search cost for this one will be 3 plus 1, that is 4, into probability of D4 equals to Q4. Okay, so Q4 is what? Q4 is 0.05. So this is 0.05 into 4 equals to 0.20. So we are doing. So in this way, we can find out the expected search cost for each node, and we can consider them as contribution to the expected search cost, total contribution to the expected search cost. So we can take the sum of all this and we are getting 2.80. Okay, similarly, we can find out the expected search cost for this tree, and we can calculate that expected search cost is actually 2.75. Okay, so even in structure wise, this tree, the depth of this tree is smaller than depth of this tree, but the expected search cost is actually we are getting lesser than this one. Okay, for for this tree. So from this one we can conclude that always an optimal search tree we are looking for that will not be in least depth or least height among all the trees. Okay, and other thing is also that if we put the key with highest probability, because highest probability means the searching for that particular key is maximum. So if we keep that key as the root, or we make it the root, so it will not actually indicate that it will be the optimal binary search tree we are looking for. So here the highest probability is key for key K5, but even if we see that with root K5, the minimum search cost we will be getting, that is 2.85. Okay, so that also indicates that if we keep the key with highest probability value as the root, so even it may not give you the optimal structure. Okay, so in this way you can calculate the expected search cost for different optimal binary search trees. So if we see that if we calculate the optimal so expected search cost for each of the optimal binary search tree, so it will not actually be a good idea, because this will be an exhaustive checking for all possible optimal binary search trees. So that will be exhaustive, and the time complexity, or there will be exponential number of binary search trees for a particular set of keys. So that's why if we have any scope of using dynamic programming instead of using this exhaustive search, we'll apply that. So before starting that, what we need to see in the problem, that whether that problem is having optimal substructure property. That means an optimal solution to a subproblem contains optimal solution to the corresponding subproblems. So here we are talking about like a binary search tree or tree. So if we see that T is a subtree, T is a binary search tree, and T dash is a subtree of this, where it contains Ki to Kj nodes. Okay, so if we want to find out T is optimal, then must be all the subtrees of T should be optimal. So T dash must be optimal with all these key Ki to Kj and dummy keys Di minus 1 to Dj. So if this happens, then we can say that obviously this optimal binary search tree problem contains or holds the optimal substructure property. Okay, so we will see that how it holds the optimal substructure property. So we can take any set of keys, consecutive keys Ki to Kj, where we say that the value of I and j between 1 to n. So we can have one key Kr between I to j, okay, as a root of optimal subtree, and it contains two subtrees, left subtree Ki to Kr minus 1, including the dummy keys D1, Di minus 1 to Dr minus 1, and the right subtree containing Kr plus 1 to Kj, along with the dummy keys Dr to Dj. Okay, so we are looking for the value Kr, which will divide this tree Ki to Kj into two subtrees, where Kr is the root, where Ki to Kr minus will also be optimal, and Kr plus 1 to Kj also will be optimal. So this thing proves that optimal binary search tree problem contains or holds optimal substructure property. If we get optimal binary search tree for this set of keys and optimal binary search tree for this set of keys, then obviously the optimal binary search tree for this one will be optimal. Okay, or the binary search tree for this one will be optimal. So this is optimal substructure property. Okay, now after that, what we want to find out? We want to find out that whether the problem is having overlapping subproblem property, or we can represent the solution of an optimal binary search tree as a recursive formula, or recursively we can find the solution of the optimal subtree. So what do? We find out the expected search cost uh, for the set of keys from I to J. Okay, where it contains these keys Ki to Kj. So we want to find out the optimal search cost for each of these values Ki to Kj, and finally our objective is to find out the optimal cost for E for the entire tree with keys 1 to n. This is our objective. So our objective is to minimize this value Eij. Okay. So when j equals to I minus 1, that means we are talking about a dummy node. Okay, because it will be I to I minus 1 actually. So I to I minus 1 will indicate this d I minus 1 value. Okay. So di minus 1, that means the tree we are talking about that contains a single node, dummy key, that is this one. Okay, and the expected cost of this one itself is the probability of this di1 minus 1. So we will set the value of e I minus 1, I to I minus 1 equals to q I minus 1. Okay, and the root of the subtree ki to kj is kr. So we want to find out the optimal cost for ki to kr minus 1 as a left subtree, and the optimal search cost for kr plus 1 to kj. Okay, and kr is the root. So here we will be getting a subtree containing all these values ki to k I minus r minus 1, and this subtree will contain k r plus 1 to k j. Okay, so this part will give you optimal search cost or expected search cost I equals to e I r minus 1. Okay, plus this will give you uh, expected search cost for this one k sorry this will be r plus 1 to j. Okay, and the probability of this one, because this is a part of this, so this will be pr actually. Okay, since the length of the search cost of this one, express search cost of this one, express search cost of this one, but since we are taking this one, so depth of this all these three is increased by 1, because we are taking this route. So for this entire, this will, so finally what we'll get, we will get the sum of the probability of all the nodes for this subtree, because it will increase 1. So when we need to find one particular node or key here, so we need to traverse all the nodes here or all the nodes here. So actually we need to add the probability of all the nodes present in the subtree. So that probability is denoted by Wij. Okay, Wij for L equals to I to j for all the valid keys, and for all the dummy keys L equals to I minus 1 to j ql. Okay, so we have to consider this one. So the total expected search cost for ki to kj, and kr is the root, can be denoted recursively as eij. As I said, this is pr we have taken for this root node, and this is the expected search cost for I to R minus 1 and the probability of all the nodes in the subtree, okay, and the expected search cost of the right tree or right subtree along with all the nodes, probability of all the nodes right subtree. Okay, so these three together, this one, and this one, this will give you the probability of this root and probability of all the nodes in the left subtree and the probability of all the nodes in the right subtree. So together Wij can be written as like this one. Okay, so we can minimize this expression as this one. Okay, where we are getting this from this one, getting this one from this one, and this expression together we are getting this one. Okay, so now you got a recursive expression for finding the expected search cost for an optimal binary search tree containing keys ki to kj. Okay, but one thing we need to remember that we don't know the actual value of kr because we don't know that which kr value will give you an optimal binary search tree. So that's why we need to explore all possible r values from I to j. So that's why our objective is to minimize this expression by finding a suitable r value. So it is the thing what we wanted to actually build up, like have a recursive formula for solving this this problem using dynamic program, because we know that if we are able to construct one optimal solution recursively for the optimization problem we are considering, then we are able to use dynamic program, because we can replace these things, this recursive part, by using some table structure where we store the values of optimal solutions of sub problems. So when they will be required later on, we can use them instead of recomputing them. Now we compute the expected cost using tables instead of recursively calling the same function or same procedure again and again. So here, like other problems solved using dynamic programming like matrix multiplication and longest common subsequence, rod cutting problem, in all those we have seen that we use two tables, but here we use three tables. One is for the expected search cost, another is for the probability, sum of probability of all the nodes in a subtree, and this is the value kr, the root value kr of the subtree if we want to construct optimal binary search tree for the problem. So this will give you the optimal value, the minimum value, this will give the probabilities, and this will give the root of different kr values for different kij values. So here we have three tables, this one. So here it starts from 1 to n plus 1 and 0 to, because to consider the dummy values actually. Okay, the probability of the expected search cost for dummy values also, and similarly for this one, the probability of this one, and but root will contain only n to a 1 to n 1 to n, because this will contain the valid root for the subtrees. Okay, so initially what we do for all the values ei I minus 1, this will be the probability of the dummy keys. So these are directly assigned with the dummy probability of the dummy keys, and similarly for wi minus 1, this will also contain the probability of the dummy keys. Okay, and now like in matrix and multiplication, we use dynamic programming by solving the smallest problem first, and then we go for the next level problem by using the solution of the previously solved problems. So we just go by the size of the sub problems by increasing one by one. Okay, so this indicates the size of the keys, actually, or the number of keys present in a subtree. So we will start with number of keys in a subtree 1, and then we'll increase 1, 2, 3, 4 up to n. Okay, and this will indicate, this I will indicate the leftmost key in the sequence, and j will indicate the rightmost sequence, rightmost key of the sequence. Okay, or the subtree. So, and this will control the length of the L will control the length of the sequence Ki to Kj actually. Okay, in this way we will solve this problem. Okay, so initially Eij is set to infinity to find out the minimum one, because this will indicate that this is a very high value, so we want to minimize it by assigning more smaller values again and again gradually. And this Wij is indicating the probability that we know that this is also the table indicating this one. So we will be using the previously computed smaller values, and then we will consider the probability of the two keys ki and the dummy key di. Okay, and for each value, possible value of r between I to j, that is for kr value we are trying to find out. So we need to calculate a temporary value, expected time, expected searching cost, that is for the left subtree, okay, of kr, and the right subtree of the kr, and the probability we have considered. So this is the same expression where we have developed in the last slide. So in this way we calculate these t values and compare with the calculated one again and again, so that finally we can reach to the minimum value. So this will be assigned to Eij for a particular subtree containing the keys Ki to Kj. Okay, and this will actually indicate the R value, that it will indicate the which key is actually is the root of the subtree in the binary, in the optimal binary search tree. Okay, and finally it will return E to root. So we can calculate in this way. If you see that initially for 1 to 0, for this one, you see, for E1, I equals to 1 to 0, so 1 to 0, it will give you the probability, the probability of the dummy key. So what is the probability of this is 0 actually. So probability of this one, you can say, if you have the table, we don't have the table here, but still you calculate, this is Q0, the probability of this Q0, 0.05, and you can see together. So you can see this one, D1. So from this D1, this is the probability D1. So you can have D, you can see in the table, 2 to 1, that is 0.12. 3 to 1, 3 to 0, sorry, 3 to 2, length will be 2 to 1, 3 to 2, 4 to 3, 5 to this one. This will give you the dummy keys probability. Okay, and when we want to calculate, suppose 1 to 1, so what we'll do, we'll take these two values plus the values of this one, 1 to 1. So you can see this one. So this, you can see this is what, 0.5, okay, and 0.05 and 0.10 plus 0.30, that is 0.5. Okay, 2 to 2, if we want to calculate 2 to 2, this one, so what will you take? We will take this one and this one. So it will give you what, 0.10, 0.05 plus this one. So it is 0.0. So in this way we can calculate any like this one. If we want to calculate the optimal, so we will taking this one 1.75 and 2.00 plus this one. So it will give together 1 point. Sorry. 1.5. It is like this. Okay, so actually there will be some calculation mistake, I don't know. But you see, we need to follow these rules only. Okay, so here what we are doing, we are having KR value. Okay, so we are considering this left one and this right one plus the probability of this IJ. Okay, so in this way, we can find out the probability of the expected search cost for a tree. Okay, so and this part will give you the root value. Okay, the root of the optimal binary search tree. And the time complexity you can measure from this one. Like we have 3 for loops, this one to this one. So finally, 3 for loops we are running. So worst case will be obviously order of NQ. So it is similar to the matricial multiplication problem. Okay. Uh, okay, so thank you for today. If you have any question, you can ask me now.